So here are the notes for torque and equilibrium. We're going to talk about what happens when forces make objects rotate, and then what we're really talking about when an object is in equilibrium, which we talked a little bit about when net force was equal to 0. So let's start off with torque. Torque is a rotation caused by an applied force. It's a vector, so it has magnitude and direction. The units it's measured in are Newton meters. And instead of up, down, left, right, north, south, east, west, because it's rotational, we're going to call the direction clockwise or counterclockwise. And because it's moving, we're really not going to give it a position like an angle. So it's moving either clockwise or counterclockwise. The equation is torque is the lever arm, R, times the force times the angle between the force and the lever arm. So what we're looking for when we're working with torques is where is the force applied, the distance from the pivot point. So if in your mind you have a picture of a door and a hinge, the distance from where you put your hand to open the door from the hinge is the lever arm. And we want that perpendicular force that's going to make the object move. So if you have to find the components, you're going to need sine of the angle. And if the problem is just set up so that the force is perpendicular, you're all set. So here are a couple just picture examples. And the top one, torque is force times lever arm. And it's going to be, it is that way because the force is perpendicular to the door. And the lever arm is the distance, like I said, from where the force is applied to the pivot point or hinge. And then in the middle picture, we've got a force applied at an angle. And so you have to look at the component of the force that's perpendicular, and that's going to be from the sine of the angle. And at the bottom, you've got force applied parallel to the door, which won't open the door at all, so there is no torque applied, no rotation is going to happen. Real quick reminder on how to break forces into components. We have an example where we have 300 newtons applied at a 60-degree angle to the door, and we need that vertical component. It's opposite the angle, so we're going to use sine of 60. So you take your original force, which is 300, multiply it by the sine of 60, you get 260. The lever arm is 2 meters, and so the torque on the door is going to be force times the lever arm, which is 260 times 2, which is 520 Newton meters. And remember, this is a vector, so the way we're pushing this is going to force the door to go counterclockwise. And we want to talk about balancing torques. We've had balanced forces, and now we're going to have balanced torques. And eventually this is going to lead us to the idea of equilibrium. But for this system, you've got two kids on a seesaw. If it's balanced, you've got the pivot point at the center where the fulcrum is, where that FP is. R1 is the distance of the smaller kid to the pivot point. R2 is the bigger kid to the pivot point. And W1 and W2 are their weights in this drawing. And you can see that R2 is shorter than R1 because W2 is bigger than W1. And if we set all of this up with balanced torques, we can figure out exactly how to position things or what amount of mass to place in order to balance something. So here's an example of that. We're going to have Bobby and Sally on the seesaw. Bobby has a mass of 40 kilograms and Sally has a mass of 55. We stuck Bobby 2 meters away. Where do we have to put Sally in order to balance the seesaw? And if you set up the torque for Bobby's side is equal to the torque for Sally's side, the force times the lever arm for Bobby is equal to the force times the lever arm for Sally. Plug in the numbers and you get that Sally should sit 1.45 meters from the center Remember, she's got more mass, so she sits closer to the center. Now let's talk about equilibrium. We've talked about balanced forces and now balanced torques, where they're equal on both sides of the pivot point. Now we're going to talk about equilibrium. And equilibrium is a condition where an object isn't accelerating either linearly due to unbalanced forces or rotationally due to unbalanced torques. So the sum of all the forces is zero and the sum of all the torques is zero. And then there's some special cases of equilibrium. If you ever bumped into an object, and there's a couple different things that that object could do. One of them is you bump into something and it rolls back to where it was originally. The other one is it just keeps moving away from you. And then there's one where it just kind of comes to rest in a new position and resumes its equilibrium. And those have special names. All this is based on where the placement of the center of gravity is. And the center of gravity is the point where you can imagine all the mass concentrated into one single point of the object. So you take the box that we push around for physics and you squash it all the way down to a singular point, like you do for the free body diagram. That would be the center of gravity. So the three conditions: stable equilibrium is the object rolls right back to where it started from and stops. Unstable equilibrium is the one where it's sitting at rest and you bump it and it just keeps rolling. And that might be like a ball rolling down a hill. It was sitting on the hill just fine until you got there, you bumped into it, and now it just keeps rolling away. Neutral equilibrium is kind of like a rolling pencil or something like that, where it rolls for a while and then stops. It could start up again if you bumped it, but for right now, it's just fine. So there you go. There's torques, balanced torques, and equilibrium. Bye-bye.